So, photoelectric effect. This is what Einstein actually gets his Nobel Prize for. All right, but as usual with most of Einstein's work, it's built on the shoulders of many other giants as well. So even when you look at relativity, he amalgamated a lot of work other people did and then put it together in a model that made sense. Did the same thing with the photoelectric effect and, basically got his prize for that. Okay? Let's have a look. These are the notes. There's a lot of them, but like I said, this area isn't particularly difficult. You just got to make sure you arrange everything right in your head, okay? All right, so, the outcomes that you're going to be learning, a little bit of electric fields revision, all right, a little bit of electric fields revision. Get used to this work done. This is a different version of kinetic energy, all right? So the work done in the region between two parallel plates, okay, notice here we've got, what does the long line mean? Positive plate, good. So that's the positive plate, and then you've got the negative plate there. So you have an electric field that moves positive to negative, as you can see, positive to negative. It's a uniform electric field, and a constant force is applied to a particle that is inside that field, all right? And that particle gets kinetic energy in its time between those plates as it goes from one plate to the other, all right? So I'm just making sure, I've got some notes here to make sure I don't miss anything, all right? So the very, very first thing is the conversion of, okay, for example, let's say there's 1,000 volts between, a potential drop of 1,000 volts between these two plates. You take one electron and you release it at one end and you let it move through. It picks up 1,000 electron volts of kinetic energy. That's what it is, okay? So it picks up 1,000 electron volts of kinetic energy. What does that really, really mean? It's just a nice, neat way of doing calculations super fast without having to involve the charge on the electron itself. Right. No pressure this time. See, I get nervous because of this. All right, so 1,000 electron volts of kinetic energy converted to joules is the 1,000, which is your volts, multiplied by 1.6 times 10 to the negative 19 coulombs. 1.6 times 10 to the negative 16. Don't make me do it again. 16 joules of energy. So that's the conversion. Obviously, to go backwards, you divide. Obviously, it's the same thing. All right. So that was the easy part. Yeah. All right. So joules, electron, volts. All right. Now we go on to if an electron is fired through a gap in the region between two plates, then the electric field will oppose its motion. If the electron is traveling relatively slowly, the field may stop the electron before it reaches the other side. Okay, so what they're getting at here is, what we've got here is a region, a plate that's negative, but you're firing an electron from out here somewhere. And this electron can pass through this gap. You would actually like to stay over here where the positive plate is, but if it's got a lot of kinetic energy, you're going to have to try and stop it, right? So you need to apply a voltage that could stop, that is a stopping voltage that might be able to stop this electron from getting to the other plate. And that's the whole gist of the photoelectric effect, that you take electrons and you can actually calculate how much kinetic energy they have, all right, with a nifty little apparatus. Now, this is an effect that was studied a long time ago. So I actually did a little bit of research here. The photoelectric effect, all right? So you've got Heinrich Hertz. Yes, Hertz of the frequency guy, right? Hertz, it's that. So it's named after him, okay? While detecting electromagnetic waves, he found that sparks could jump larger gaps if the metal surface was illuminated by ultraviolet light. He was like, oh, what's that about? So you shine a bit of extra light and you can get better sparks happening, way more current happening. All right, so he notices this. All right, it was soon shown that the ultraviolet light was liberating negatively charged particles, electrons, from the metal and helping allow sparks move across a gap. All right. Okay, so then J.J. Thomson showed that the charge to mass ratio of these particles was the same as that of cathode rays. Now, do we know what cathode rays are? Yes, it's basically electron electron beams, beams of electrons, okay? Did I put anything in here that was, yep. So Thomson figures out these are electrons that are actually jumping off the metal, which is awesome, all right? So then you've got, okay, so then Maxwell gets a look in as well. So you learn a lot of Maxwell's stuff as well when you go to uni. According to Maxwell's electromagnetic theory, see, Maxwell was a mathematician, right? So he was really smart. He made all these things work out. Back in the day when they were trying to figure out what's the actual speed of light, they were working it out experimentally, right? Maxwell's equations, like, oh, you just do some maths and the number 3 by 10 to the 8 comes out. And you're like, he can derive the speed of light. And that was back when they realized the experimentation and what Maxwell's equations were doing was like, they were the same thing. And they were like, oh, it's a beautiful confirmation of what they were doing, all right? So Maxwell, let's see, what did I write? Maxwell, he basically showed that light carries energy, so should be able to liberate particles from the metal, all right? So if light carries energy, then it should be able to rip electrons off a metal. That's what Maxwell showed. Then you've got Philip Leonard. So in 1902, Leonard carried out a detailed study of the photoelectric effect, examining the kinetic energies of photoelectrons. This is pretty much what you learn in this chapter. This is the results of what he calculated is what you're learning here. All right. So the electrons have been emitted from a metal using light. So we call them photoelectrons. They're exactly the same as any electrons. A current that is created by light shining on a metal, we call it the photocurrent. Is it different to normal current? No, it's just current. But when we say photocurrent or photoelectron, we're just saying that it's there as a result of light illumination. Light is doing it. It doesn't have to be visible light. It can be ultraviolet light, any light that works for that particular metal. All right? Okay, so yeah, this is all about the idea of electrons being ripped off metals and are allowed to flow. All right? That's what this is about. Good.
Because of like the perpendicular magnetic field.
No, we don't really use that to explain this effect. See, we do light. We talk about light as the wave-particle duality of light. That's how we talk about it, right? And there are some experiments like interference and diffraction. You're like, oh yeah, that's light. That's a wave. But the problem was, right, when you were illuminating a metal with light, a few weird little results popped up. They were like, if I just shine intense light on the metal, eventually electrons should pop off. Eventually. But they don't. They don't. No matter how much you shine or how intense you make the light, you don't get the photocurrent, you don't get those photoelectrons happening, no matter what. That led to the idea of like, oh, so light, the frequency of the light was more important than the intensity of the light. Now, if light was purely acting as a wave, then it wouldn't matter. You could just like hammer the metal with any light. Eventually, you're going to get electrons coming off. But like I said, that's not what they found. And they started to think, wait a minute, if the light's the wrong kind of light, it's never going to get that effect. There's never a delay in the effect as well. And that's something that they often ask for in like multiple choice type questions. How do you know, what's evidence for the photoelectric effect is really a wave nature, it's really a particle nature of light. What we're saying is, remember that little drawing of light that I gave you, where you imagine light as a particle, as a little photon. So when we say light is a photon, we're actually saying light is a particle, not a wave, okay? But what we've said is, each photon retains its wave nature, as in it has a frequency. So photons of green light, photons of purple light, they all have different energies, all right? And so what these early experiments showed was that you could actually calculate the energy of this individual photon using energy is equal to Planck's constant multiplied by the frequency of the light. That tells you how much energy in joules or in electron volts, that photon of light actually carries with it. Now, if that photon carries enough energy, it can rip an electron off a metal plate and make it fly away. Give it some kinetic energy, all right? This is the particle model for light. And that's what it alludes to. Now, this effect, when you throw these photons at a metal plate, The effect occurs immediately. There is no delay, as a wave model might suggest. You know, kind of like the metal's heating up. But no, it's not heating up. No, if the light is correct, that packet of light, that photon, will be absorbed by a single electron in its entirety, yeah, like a particle, not a wave, all right? And if that energy is enough, it will be absorbed by the electron, and the electron will break its bond to the metal. There's a certain binding energy in there. It'll break its bond to the metal and fly away with some kinetic energy. That's what this model is saying, all right? And that's how it's different. That's why there's no delay. You shine the light, you get the electrons. Switch the light off, the electrons stop. That's it. If the photons have a frequency that is too low to actually rip electrons off that particular metal, it doesn't matter how many of those photons you throw at that metal, you will never get electrons off it, okay? Because remember, let's say the metal surface is sitting here. Electrons are sitting here dancing around connected to the metal, all right? They've got little binding energies holding them close to the metal. That single electron must absorb that entire photon in its entirety. Okay, so it must absorb the photon in its entirety. That energy has to be enough to break that link. If it's not enough, then it's just not enough. You can't go, I'll just hit it with this photon and another one, and no, it doesn't work that way. One photon goes into one electron. If the frequency is high enough, in other words, the energy is high enough, you'll break the bond of the electron will fly away with some kinetic energy. Let's say the electron is being held by 10 joules, or like it takes 10 joules of energy to break the bond, but you hit the electron with a photon of 20 joules. I'm just making this up, there's no such thing, right? Let's say I hit the electron with a photon of 20 joules. How much kinetic energy would the electron have after I broke it free? Yeah, yes, that's exactly how it works. So if it's 10 joules of energy to break the bond, but you hit the electron with a packet worth 20 joules, yes, 10 joules is used up in breaking the bond. It's still got 10 joules left. What's that 10 joules show us? Kinetic energy. You can figure out how fast it's moving, right? By doing that. So that is the basic premise, and you have learned in this topic a few little funky equations to let you do something with it, okay? All right, so Leonard puts all this together, and then Einstein comes in at the end and links together Hertz, Thomson, Maxwell, and Leonard's work and goes, oh, here's a model of how all this works neatly. That's what he writes his paper on, and that's why he got famous for that particular thing as well. Although most people think he was most famous for relativity, but he did more than that. Okay. Main experimental results. Let's see. Oh, okay, here we go. The main experimental results. These are the things that get quoted, and I put on your help sheet as well, okay? So you can read through them. The main experimental results were the rate at which photoelectrons are emitted is proportional to the intensity of the light for light above the threshold frequency. All right, so what does all that mean? Okay. So, for example, like I said, if I was throwing light that was 20 joules at an electron that only needed 10 joules to liberate it, as long as I'm throwing photons of energies that are higher than the binding energy, then I'm going to be getting all these electrons popping off and flowing, right? So you can detect them with like an ammeter, all right? So I'll get them. Now, if I throw more photons, then each photon lines up with an electron. More photons, more electrons. So in that respect, as long as the energy of each photon is higher than the binding energy of the metal, if I just keep adding more photons, making that more intense, I'll just get more electrons because there's more opportunities for electrons to suck up photons and fly off, okay? Drop the intensity, I'll get less electrons. Makes sense, right? But only if the energy of the individual photons is higher than the binding energy, that all works, all right? If you're hitting it with photons that are 5 joules when you need 10 just to break the link, you can throw billions and trillions of them at them. You're not going to get any electrons, okay? Yeah.
So is it one photon gets 1
Yes, one photon is absorbed in its entirety, and that's the gist of the particle model of light, where light is like, oh, it's not just a continuous thing. No, it's like its own little packet. And even Newton discovered some of these weird effects, even back in the 1700s, and he's like, oh, the corpuscle, the corpuscular. You know, they used weird words back then, but yeah, to say that light was acting as an individual packet, Henry?
The photoelectron is the same as a regular electron.
It is. It's just that it was liberated by a packet of light. That's all. That's the only difference. Yeah?
Could it be two?
No. One photon for one electron. And in reality, you can throw if you could throw trillions of photons at a metal surface, you might get millions of electrons because they're not all going to do it. You know, there's all those weird interactions between matter and light. It's not one for one. It's like perfectly efficient or anything like that. You know, you might have to, like I said, billions and trillions of photons to get, a few million electrons that actually land properly and get ripped off. You know what I mean? It's not a one-to-one thing, okay? All right, cool. There is a simulation here which just wouldn't load the other day. Okay, but that's not particularly important. What is important, though, is here is the standard picture that you see of what the photoelectric effect apparatus might look like. Now, this is a picture that we often see. I actually downloaded one which is better. This one. Okay, so here we've got something that looks a little bit more real. It's still a stripped down version of it, but... Sorry? The gauge. Yeah, the voltmeter. Oh, I'm sorry, you're asking what that thing is. It's an ammeter because it's measuring the current that's actually coming through. So what have we got here? What are we actually looking at here? Here you have a metal plate that you're investigating, okay? The metal plate is being investigated. So you're going to shine light through this glass tube. Inside the glass tube, it's supposed to be evacuated, like almost a vacuum, so that the air in there doesn't interfere with what's going on, okay? So light comes in through the glass, illuminates the metal. If that light is of the appropriate frequency, you might get electrons being broken off the surface and flying across. Now, what's the point of the battery? Excellent question. The point of the battery is so you can manipulate these electrons and see how much energy they actually have, all right? So let's say I connect this battery. Usually the battery is shown as a variable power supply. So you can make this terminal neutral. You can make it neutral. So there's no voltage in this system at all. Or you could make it negative. So, for example, you can make this plate negative. So if you liberate an electron from this plate, it's going to want to get away from there, right? So if I make this plate negative, it means that if I get any electrons coming off at all, if I've gotten right down to that frequency where the effect just starts to happen, right? Then I should be able to read it in the ammeter. Should be able to read a flow of electrons just moving through, okay? If I want to help them. But let's say I keep now ramping up my frequency, and so I'm giving each electron more and more energy. Kind of doesn't need any help anymore. It's going to fly across because it's got heaps of kinetic energy, no problem. So I'm like, well, how much kinetic energy? All right, so what I can do now is I can flip this around and make this plate more and more negative, make it more and more repulsive to electrons, to the point where I can control this voltage, and I'm watching this arrow. So if I'm using a frequency of light that's giving me heaps of current, I can figure out what the highest kinetic energy of the most energetic electron is, all right, that comes across. The way I do that is I keep making this more and more negative by more and more voltage, raise the voltage, potential difference between the two. Make this as negative as possible. As this gets to a point where it becomes so negative that even the most energetic electrons coming off this metal using the specific light that I chose will not make it. At some point, they're just going to go, I don't want to eat it. They're just going to come back, all right? So at some point you get nothing. And that tells you, at whatever voltage that was the stopping voltage. That was the voltage required to actually stop. So that voltage, now you know how it works with electrons. So if that's 10 volts, that's 10 electron volts. That's how much kinetic energy they had. They had 10 electron volts if it took 10 volts to stop them. So to get this needle to drop to 0. All right? And so on. So, yeah, can
It's just for the specific frequency, right?
It's for that specific frequency, yes. Because there's also, don't forget, there's also the fact that the metal is kind of layered and three-dimensional. Electrons are buried deeper in the metal. Some are very close to the surface, easy to liberate. So this is really about stopping the ones that got the most energy out of your frequency. All right? And that's the answer usually that you're looking for in these questions. All right? And there's a nifty little equation that you use, which is super simple to do. All right? What you're looking at here is the vessel, the plate under investigation. There could be magnesium, zinc, it could be potassium, it could be anything. All right? Light comes through. If electrons come off, you can say, oh, okay, there's enough light, there's enough energy in those photons to get electrons. How much energy are the electrons actually getting? Well, I'll start making this plate more and more negative until the current drops to 0. And then I know what the maximum kinetic energy of those electrons jumping across is. That's the same exact diagram as what I just showed you. Yeah?
Is there different bonding strength?
Yes, different metals have different binding energies. And yeah, we're definitely going to get to that. That's actually kind of nearly the next thing. And so there are two things, yeah? There is a binding energy that is specific to the metal, and there's also a threshold frequency where the effect just begins. And we basically call it F0. So if you want to know how much what the binding energy was, okay, well, you can calculate that by going, where does the effect just begin? And right there. So where the effect just begins, you're looking at the electrons have been broken from the metal, but they have almost 0 kinetic energy. They can't actually move. So obviously, if you're doing this for real life, you'd be graphing this information. Because obviously, if the electrons have 0 kinetic energy right at that frequency where it starts, how can you possibly detect them? You can't detect them. But what you do is you keep ramping up your frequency and you end up drawing a nice, neat graph, and then you can extrapolate the graph back to exactly what it is. And that's how you can find out what that actual threshold frequency is. All right? So if I move through here, okay. All right, so this page is trying to get you to realize what's important to the photoelectric effect and what is not important to the photoelectric effect. Okay, so over here, let's see. Red light, low frequency, no electrons emitted. Bright red light, same frequency, still no electrons. Doesn't matter how bright that light is going to be. Why? Because individually those packets of light do not hold enough energy to even at least break the binding energy of the electron. So you get nothing no matter what, okay? Now you move on a little bit and you can see green light, electron emission starts. Because we know green light is higher energy than red light. It's got a higher frequency. And by this, we know that means more energy per packet. But now all of a sudden we get a small current. We're just using, some dim green light, okay? But now that the effect happens, okay, by increasing the amount of light that you're putting on there, you'll get more current simply because there are more packets of light to liberate more electrons. So more electrons, more current. That's what it means. As long as the effect starts, then you can manipulate it with intensity. As long as you have enough energy to break those individual electrons free. Okay? All right. Now I'm going to move it up again. I'm going to go from green light to purple light. Even more energy. Okay? Ultraviolet light. The electron emission continues. Okay? The electron emission continues, but what are you doing? Why are you moving? Don't move. That's not what I want. Okay. Down. All right. All right. So, more purple light. Again, you get more. But what's the difference to the electrons themselves, now that I've gone from green light to purple light, what?
More energy.
Yeah, they're more energetic. They've got more kinetic energy. Because the leftover of that packet, the leftover after absorption is so much greater than the binding energy was, that now those electrons are like super fast, okay? Way more kinetic energy. Yeah.
The light packets disappear.
Oh, well, yeah, they're absorbed into their entirety, and then what can happen is then they can also be emitted as well later on, okay? Yeah?
So is the reason why you can't just buy two photons of the same electron because it spreads throughout the metal, like the energy?
It's more to do with the nature of the electron itself. You see, when you get to a point where electrons are a particle that is super small, right? What you find in the next chapter after this is that electrons themselves can be modeled as a bit of a wave themselves. So they had to come up with a model. They had to come up with a model that explained, well, how does a bit of light go into an electron? What does that even look like? What is that supposed to be? So what you find as we move on through this chapter, not this chapter, the next chapter, is that if you model the electron itself as having a sort of a waveform, then that's the part of its nature that actually absorbs that packet of light, and it ends up sort of creating a waveform that's bigger than it was before. And so it creates basically a standing wave when it absorbs the right kind of light. Yeah?
So if it absorbs not quite enough light, should it still absorb the
No. If it's not enough to break it free, it basically ignores it. And so it goes through, it's not right, it's just not going to do anything nice, it's not going to reinforce, and it'll just go past. And it'll only start happening if the light is of the right sort of frequency and above. All right? Okay, so that's what these diagrams are. And I don't want to bang on for too long because I know you guys get really tired, and so I want to make sure we go kind of quick. All right, okay. So as the anode is made more negative, fewer electrons get across the tube. This means that the ejected electrons must have a range of kinetic energies. All right, so they don't all come out with the same kinetic energy. You're only ever looking for the maximum kinetic energy. All right? Yo.
Do we also look for like the minimum? Or just
The minimum. The minimum is where where the effect just happens, and that starts lending itself to the threshold frequency.
So it's just max.
But the calculation is usually just for the maximum kinetic energy, right? So, but you do get a range of kinetic energies, all right? That's why it can drop and increase, all right? So electrons with little or no kinetic energy are stopped as soon as the anode becomes negative. Those with the most kinetic energy are stopped by V naught. Looks like V naught volts. Energetic electrons come from the surface. Less energetic electrons come from below the surface. The value of V naught, it's not V naught, it's VC. Sorry, VC, is the cutoff voltage. You reach that voltage where you get zero current now, and that's the cutoff voltage. All right. Now, there's a nifty little graph that we use to describe this, and this pops up in exams like pretty much every time. All right. This is a graph of photocurrent, in other words, current, and voltage. Over here, if the voltage is positive, that makes the anode it makes the collector super attractive. It really wants the electron. If there's an electron there, it's going to get it. Hence, the graph itself plateaus because it plateaus at where there's pretty much every electron that you release. You make the plate positive enough, those electrons are going to find their way there, right? So that means you get to that maximum number of electrons, the current, and that's where it plateaus, okay? Now, this is, say, green light. If I make bright green light, I get lots of current, lots of photons, lots of electrons. That's all that means. If I reduce the amount of light, I get less and less current, okay? Because just less photons, all right? That makes sense. But if I get back here, I make the potential between the collector and the emitter zero, and then you can see there should be like a little drop here. And then if you start making the collector more and more negative, less and less attractive to those electrons, the current starts to drop because you're throwing back a lot of those electrons. They're not getting all the way to the collector. So the current starts to drop. And this is just the idea of me taking the battery and just making it more and more, making this part more and more negative until that needle drops to 0. That's me, making that collector more and more negative until the needle drops to 0. See it? I was like right in front of the camera for that part. Okay, so as the collector gets more and more negative, the current starts to fall off because it's just harder and harder for those electrons to get there. But the stopping voltage for all 3 versions of that green light is still the same. Why? Because that was the maximum kinetic energy available. You couldn't do any more than that. All right? But if you move on to the next graph, you can see that here what we've done is we've changed frequency, which also changes stopping voltage. Now see if you can interpret what this graph is telling you. Okay? All right. Let me just... Packets of light that are green, blue, and purple, which one has the least amount of energy? Like per packet, per photon. The green has the least amount of energy. It's the lowest frequency because it goes up in the order of the rainbow. Okay. This one has more kinetic energy, and this one has the most kinetic energy. Right? Now, notice to have a really, really high photocurrent, okay, it means that this light is really, really bright. But individually, the packets of light that are coming out of the light source actually don't have a lot of energy. So you can see it doesn't take a lot of negativity here to stop the most energetic electrons. So yeah, this is a bright green light, but individually those packets, they're not carrying heaps of energy individually. Okay? The next being the blue light. The blue light, this is kind of dim, it's medium brightness. Less photons themselves, but individually those photons carry way more energy, okay, individually. And each photon can only be absorbed by a particular electron. Now, those electrons, because now they have way more kinetic energy because that light carries individually more energy, because it's frequency, you've got to make the plate even more negative to stop the most energetic ones. See how that works there? All right? And then the last one is this is the dimmest light, so you don't get a lot of current, okay, because there's not a lot of photons doing any work. But individually, it's the highest frequency. These are the hardest to stop. Look how negative the plate has to be before you stop the most energetic of those electrons. Yeah. So you get an idea of what the graph is actually telling you, right? Brightness will tell you how much current, but the stopping voltage tells you how much energy individually those packets carry. Yeah?
You said earlier that the frequency has to be similar to the movement frequency of the electrons. Does that mean that you have it so it's too high frequency?
No, not in this case. There are 2 effects that we study here. One of them is this photoelectric effect where the electrons are ripped off and they go away. In the last chapter, okay, in chapter 20, you're talking about electrons that are still bound to their atoms, but when they absorb a packet of light, they just jump up energy levels and then jump back down again. They're still bound to their atoms, okay? So what we're getting at there is, for those transitions, the energies are very, very specific. They have to go up and down specific amounts, so you'll see that, okay? But when it comes to this effect, you've actually given it so much energy, you've taken it away from the atom completely, and therefore it can absorb, there is no real, limit to how much it can absorb. It just shows up as excess kinetic energy. There are very classic types of questions that they ask you, all right? And often they are the comparison between the wave model and the particle model, all right? So where the wave model failed to account for the photoelectric effect, why they went looking for the photoelectric effect in the first place is because they were just seeing things that you just couldn't explain with the model they had, right? So the electromagnetic wave model describes the energy in the light beam as arriving continuously and uniformly over the metal surface, and that couldn't account for the photoelectric effect, all right? I don't want to read all of this. this because I've kind of explained a lot of that already. But the photon model was a much neater explanation as to what was going on, individual matter interaction. So in 1905, Albert Einstein extended Planck's idea and suggested that light was not merely emitted in discrete amounts of quanta, but it retained its identity. This is why we draw it as a little circle with waves in it, because its little waves are its identity. It still is the frequency that it is, but it's traveling as a discrete packet, okay? But it retains its identity, traveling through space as a particle of light energy or a photon is ultimately absorbed by matter as a complete thing. All right, lovely. Okay, now there's a little bit of maths, which is kind of the good part, especially when we can add up like decimal places very easily. Okay. We all saw that. So in the photoelectric effect, one electron could absorb exactly one photon and receive the full quantum of energy. Okay. All right. So this is what I've written. Here we've got the energy of a photon of light is this. E equals HF. All right? Nice and neat. Energy of an individual photon. Okay. So why did I write that? All right. H is equal to 6.63 times 10 to the negative 34. Is that joule seconds? Or 4.14 times 10 to the negative 15 electron volt seconds. And they're on your help sheet as well. All right? These are Planck's constant. If I use this one, this answer is in joules. If I use this one, this answer is in electron volts. That's it. All right? So you look at the little box at the bottom of the question, and if there's a little EV in there, you know which Planck's constant you're using. Please be careful, because you're going to end up doing a sack on this. And of course, there's always someone who uses the wrong one and gives the answer in the wrong form, when it just specifically says which one to do. Be very careful, all right? It's attention to detail. All right. So here is the formula that we all know and love. The maximum kinetic energy. Now this makes sense if you watch really carefully.
Sorry, there's some year
This is the maximum kinetic energy of a photoelectron is equal to the energy of the wave packet or the photon that you threw at it, take away the binding energy, or what is often referred to as the work function of that metal. And they're different for different metals. Okay, so in other words, the little chain that's holding that electron to the metal, how much energy does it take to break that chain? That's that.
Is it actually?
No. It is not an actual chain. I just like to imagine it as a chain. All right? So, now this formula looks really simple. And when I just explained it, everyone went, yeah, that makes sense. And it did. It's fine. Yet, there are nice little ways where you can confuse yourself and end up answering the question thinking that you're looking for one value when you're actually looking for the other. You've got to be really, really careful with this, okay? This is the maximum kinetic energy. Max kinetic energy. This here is the energy of the photon. And this is the binding energy. Now, this leads us to this funky little graph. All right? Experimental confirmation of the photon model. Okay? Here we've got Millikan. We've all talked about Millikan before, remember, with the little oil spraying particles. So Millikan, I believe, identified the elementary charge. He figured out that, yes, electrons were 1.6 and that any charge...
1.6?
Yeah, I'm pretty sure it's 1.6. So I've said negative 70? No, 19. All right. So Millikan kind of figured out that, yes, that all charges were multiples of 1.6 by 10 to the negative 19. All right, he figured that out. So now he's also gone on and done this. Now look at this graph. This graph has a couple of things, and yes, you do kind of need to know this graph. This graph has the energy of the electrons. All right. Actually, what I'll do, let me just, so imagine this is what's happening with this graph. This is the individual kinetic energy, the maximum kinetic energy of the electrons from the effect. All right. This graph and this graph are totally different. Okay. They don't tell you the same stuff. For example, in this graph, you've got intensity. Intensity is shown on the graph and how much current you get. If you look at this graph, nowhere does this graph give you intensity. It doesn't care about intensity. It's a graph of individual electrons. So don't mix them up. Don't try to use one for the other because, again, the more practice you do, the easier this is. All right? Okay. So you're firing light at this metal that's of a frequency. Notice this is the frequency here. Of a frequency that is way below where the effect begins. So nothing is happening, hence thus therefore the graph is dotted below here because this kind of represents negative energy and we don't do with negative energy. All right? So as your frequency goes up, all right, all of a sudden you hit F0. F0 is the frequency when this just begins. All right? When the effect just begins. Now you start to actually see dots. And that's what often you'll see. Some questions will just give you a series of dots and ask you to do like a line of best fit and calculate some value out of that. All right? So, but the rest of the graph is just extrapolated. Now, this here is F0. Now, F0 is where you've just broken the bond. So guess what? You can take this formula, EK, the kinetic energy, is equal to HF, take away HF0. All right? So they slip that in sometimes. And if you never looked at it, you're like, what the hell is that? And you get all confused and stuff. It's like, no, that's F0. F0 is the threshold frequency. So this is the frequency or the energy required to break the link. Okay? So as long as you've given it more than that, you should have some kinetic energy in that electron. All right? Easy. It's a very easy mathematical relation. You don't have to know anything more than that. Okay? Now, another version of this. EK is equal to, we can do this, F minus F0. So, because the physics people are very mathematical, they love throwing weird versions of something that you saw that in your notes, and your teacher was crap and didn't tell you about the rest. And then you get really confused all of a sudden because they've done something mathematically not expecting, all right? But really, they are all equivalent. They're all the same thing. Yeah, man? On the graph, it's just F0 because this is frequency. But so you can read that frequency. So this is about 5.5 or 5.4 times 10 to the 14 hertz. So if you took that value and multiplied it by this Planck's constant, 4.14, you would get, basically, you would get the energy required to break the electron free of the metal. Yeah.
It's like a gradient of that.
Absolutely. And that is one of the standard questions that they give you on Saxon exams, is that this gradient, notice the gradient's always the same for all metals. Yeah, because the gradient is Planck's constant. So when you get a question with some dots and a line of best fit, they get to do a line of best fit and calculate Planck's constant. If you just write down Planck's constant, you'll get the question wrong. They don't want that. They want you to actually do rise over run, okay, and figure out Planck's constant. Their Planck's constant they gave you will always be something weird, a little bit different to the accepted values. They do not just write down Planck's constant, like, yeah, it's the gradient, I need to work it out. It's like, no, you need to work it. That's what they're testing. They're testing that you know that it's the gradient and that you can do rise over run. That's it. All right, so please don't do that. All right, now, one way to imagine, oh, that's that value there. These values tell you what the maximum kinetic energy is of all of these different all of these different photons frequencies. But when you extrapolate all the way down to here, the intersection on the graph is the work function. So for example, if you're trying to work out this equation because maybe you're trying to find maximum kinetic energy, or maybe they gave you the maximum kinetic energy and they give you the graph, and they say, well, how much energy was in the photons of light that you were using for that kinetic energy? Like, oh, but I need the work function. Where am I going to get the work function? Here it is. It's just the intercept on the y-axis, basically, on the energy axis. So that would be 3.7. And yes, their answers are they always give you answers within a range, okay? So you don't have to be exactly perfect all the time. You have to be in the ballpark when you're doing questions like that, all right? So that's probably about 3.7 or 3.8. Over here, this is about 6. I just call that 6. So what is the binding energy? 6. So take away 6 electron volts, as in 6 electron volts. That's what it is. Occasionally, there'll be joules here, just to see if you're like awake, I guess. But 99% of the time, it's all electron volt calculations, all right?
Wouldn't that be H minus W?
Oh, it is. Yeah, the minus. And remember what you're doing. You're trying to figure out, there is no real negative energy. Even though these negative energies are down here. So I did read once, imagine the electron is in an energy well, okay? And you need to raise it before you can take it away. All right, so you need to pour energy into it to raise it to the top of the energy well. So light has been shown to have momentum. All right, so momentum of a photon. Okay, so the momentum of a photon is calculated by momentum is equal to its energy divided by the speed of light. Okay, and basically you've got a couple of other results using the wave equation. The wave equation V equals F lambda. When it comes to light, C equals F lambda. All right, and what you can then do is from that result you can have HF over C, and you can also have H over lambda. All of these results give you the momentum of photon. All right? Now, that also gives us one more version. That gives us one more version of the kinetic energy formula, which is EK is equal to HC on lambda. Take away any of these versions, W, HF naught, whatever. It's just, the work function. So you've got all of those that you can look out for. And I think I put them all on the help sheet just to make sure that it's like there in front of you, just in case. All right? Momentum works exactly the same as any other momentum. So the most typical kinds of questions for momentum is, okay, so you've got light, you've got a photon of light with this frequency or wavelength, and what's the momentum of it? So you calculate momentum. Okay, what's its change in momentum when it hits a perfectly reflecting surface? Okay, so what's the change in momentum? Well, its change in momentum is final momentum, take away initial momentum. It's exactly the same as normal momentum, all right? The only other version of that is now the mirror is taken away and replaced by a perfectly absorbing surface. You know what I mean? So, okay, what's its change in momentum now? Okay, final momentum 0, take away initial momentum. It's the same momentum calculation. Just the numbers are really dodgy looking because it's like, it must. Wow, you really think about things. That's good. I came up with a couple of examples here. Example 13. Oh, no, not 13. Example 3. Why did I pick example 3? Okay. This stuff in action. The graph shows the maximum kinetic energy of electrons ejected from different metals as a function of the frequency of the incident light. It's basically saying the graph is. All right. What can be deduced from this graph? The maximum kinetic energy of ejected electrons is proportional to the number of photons incident on the metal surface. Can that be deduced from this graph about the number of photons? No, this graph doesn't give you intensity. It doesn't tell you how many photons. It's just, remember, individually about the kinetic energy, for God's sake. All right. Then, what's the next one? More photons are required to cause an electron to be ejected from zinc than from potassium. more photons. That implies that you need to hit the same electron with lots of photons. No, that can't be right, okay? C, any photon that can eject an electron from the surface of zinc must also be able to cause an electron to be ejected from potassium. So, if a photon can get an electron off zinc, it definitely can get an electron off potassium as well. Does that make sense? Hell yeah, it does. If you extend the graph down for the rest of it, you can see how hard is it to lift the electron out of its well. Well, it's harder to get an electron off zinc than it is off potassium. So if you can get off zinc, you definitely get off potassium. So C is correct. All right? All right. And for any given frequency that causes electrons to be ejected from all three metals, the number of electrons ejected is always the greatest for potassium. Well, again, that doesn't really say that. The graph doesn't really say that. Think about these things. Right. Example 5. What is the energy? Listen. What is the energy of a photon of wavelength 580 nanometers? Again, simple little calculations that people still love getting wrong. Okay, so what's the formula? What formula are we using? E equals? HC over lambda. Now, people still to this day look at the nanometers and use it as frequency, or vice versa. You've got to be careful. You cannot use nanometers and frequency interchangeably. They're not the same thing. All right? So, also, as lambda increases, does the energy increase as well? No, it doesn't. Yes. See, that's another one that people do all the time. As lambda increases, what happens to the energy? It's like, oh, increases. It increases. No, if lambda's increasing, the wavelengths are getting spread apart. Your frequency's going down, not up. All right? So don't link those two things together because then they don't go together. All right? Be very, very careful. They love doing that because they know kids will just automatically go, oh, increase, more, bigger. No, that's not what it means. All right? Okay, pardon? In a minute. And that was example, example 6. Example 6. A laser has a power output of 30 milliwatts and emits light with a wavelength of 650 nanometers. How many photons does this laser emit per second? So what's watts? What's that telling you?
What?
Exactly. What's watts? What is it telling you? What is the watt?
What's what?
Thank you. Joules per second.
And you just kept going, what's what?
Joules per second. All right? So, when it asks how many photons are being emitted per second, they're basically telling you it's 30 millijoules per second is coming out of the laser. All right? Now, you know that that laser is made up of discrete photons, all of the same frequency. So you need to figure out how much energy does each one of those photons contain, right? Then you say to yourself, well, I know how much energy is coming out of the laser, 30 millijoules per second. Divide that by how many joules is each photon. That tells you how many photons are coming out every second. It initially looks like a kind of tricky question, but when you know what it's actually asking, it's super simple. All right? All right. So, that, I believe, is the end of my script. I think that is the end. All right? And then on Thursday, we will do some questions and get our heads around it and actually try this stuff out. All right?